Welcome everyone to tonight's webinar, Code by Numbers, brought to you by Texas Instruments Australia. Let's have a look at what we're going to cover in this evening's session. Code by Numbers. We've got 4 activities that we're going to cover. The first one is called counting factors, and we'll do a little bit of pseudocoding in there. The second one is Euclid's Algorithm. The third one is the Euler Totient function. It sounds scary. It's not. It's actually pretty cool, and there's a lot you can investigate. And finally, highly composite numbers. These activities are designed primarily for a middle school mathematics program, preferably an elective study, but it doesn't have to be, but it certainly complements and enriches a somewhat crowded curriculum, often referred to as an inch deep and mile wide, or perhaps I should say 2.54 centimeters deep and I think it's 1,609 meters wide. Peculiar. These activities encourage active engagement. So what does that mean to have active engagement? It means a lot more than answering a series of textbook questions that quite often equate to just rehearsal. Active engagement in this context means that students are posing questions. They're creating and testing hypotheses. They're recording and reporting on their findings. So there's a lot. The other thing these activities cover is a little bit of coding, a combination of pseudocode and also actual coding. There's a couple of options. So if you're more familiar with basic, TI basic, you can use that, or Python. Certainly the students enjoy Python. I'm fairly new to it, so I'll see if I can give it a crack later on during the session. We'll see how we go. Each activity also includes an investigation, which means it's perfect for students as they progress into the higher levels of maths, particularly if they're, say, doing VCE mathematics, or in Queensland where they might be doing, say, a problem solving and modelling task. So investigations in each one, and they're not trivial. They're certainly not trivial investigations. So let's have a look at why would you even bother to code, even if it's not in your curriculum. There are many reasons why we should include coding. Critical thinking is one of them. Reasoning and problem solving. They're all naturally a good part of mathematics, and they're certainly covered when students try and write code. A really powerful one is the ability to contextualize and decontextualize a problem. That is, by getting something in the real world and extracting it just to some pure logic, constructing that algorithm, generating an output, and then relating it back to what the original problem was about, which we do a lot in maths. That's usually the last couple of questions in an exercise, the ones that the kids really have difficulties with, where the instruction is not explicit, such as solve or factor or expand. It also encourages students to persevere on a problem. Coding can be very challenging, and very rarely is it done within a couple of minutes, unlike, dare I say it, some textbook questions where the students are literally just churning through them very, very quickly. In the real world, a problem that only takes 2 or 3 minutes is not really a problem, it's a task. Problems often take days, months, years, or maybe never get solved. So having students persevere on a problem, it comes naturally in coding. It also encourages students to design, build, and test, which is why we often see coding referred to in STEM. This idea that you'll design some code, that's the pseudo-code part of it, then you build it, in other words, you actually put it on some sort of a platform where you need to have the specific instruction set akin to whatever language you're using, and then they test it, much the same as an engineer would test structures and so on before they actually go and put them out there. So that's why it's included in a STEM course. And if we think about neuroscience, this ability to chunk, and this particular series of activities, Code by Numbers, is designed to be progressive. That is, by the time the students get to the last activity, they're going to need resources from the first couple of activities. They're all linked and tied together. So this idea that, say, for example, a highest common factor, the students can write code to do that. And then in the last activity, you'll see the student just has to think, oh, if the highest common factor is this, then I can do that. And by that, they're chunking. They're not going down into the algorithm what is required to find the highest common factor, just that I know if the highest common factor returns this particular value, this is how it gets interpreted. If we think about senior level mathematics, say for example, where calculus is involved, students often need to generate an equation, which ultimately they're probably going to differentiate or integrate, whatever that might be. But in the process, they might have more than two variables. And therefore, they have to think, how can I eliminate a variable, such as perhaps simultaneous equations? So the whole process of simultaneous equations is just chunked away. I'm not sure whether I'm going to use elimination or substitution. I just know that I can use this procedure to eliminate a variable or two, and even how many equations I might need, depending on how many variables I might have. So that's what we mean by chunking, this ability to make a quite complex problem and break it down into small pieces. So let's have a look and get started on these four activities. The first one is factors that count. It's actually been on the Texas Instruments website for a number of years. It's been downloaded about 1,000 times, but I've rejigged it just a little bit to kind of cater for this particular group of activities. So what do the students need to do? Ultimately, they're going to come up with some sort of a rule that determines the quantity of factors for any given number. So, given that I want participants in this session to get actively involved, here's your first question. Determine the quantity of factors for each of these numbers. Now, we're on time constraints, so I'm going to be quiet for a moment, and I'll just get you to choose one of them and put your result in the chat. So try 36, how many factors does it have? 100, how many factors does that have? Choose one of those numbers and let us know in the chat how many factors does your number have. And right about now, I really need someone saying, use factor on the CAS. Well, yes, you could. You could get the prime factorization, that's for sure, but it doesn't tell you the quantity of factors. So I do like the idea of use factor, but we want to know the quantity of factors. If you already know the formula, then you can certainly use that factor command. So let's see who else has got. Someone's put in the chat 9 factors. Very good. So one person said that 36 has 9 factors. Let's see, has anyone tried factorizing 100 to determine that? Another person says 9 for 36. Someone said 8 for 36. They may have missed one of them, because one of the things we know about perfect squares, and this is something the students discover in this particular activity as well, is that perfect squares have an odd quantity of factors. Someone else has put in 7 factors for 100. I think you'll find there might be 2 more. Well, actually, they're not. It's not mine. There will be. And here's one of the reasons why we actually want to use some coding, because it's so easy to miss a factor, or 2 factors in some cases. So when we're trying to find a rule, our whole idea is going to be thwarted if some of the information that we're getting is wrong. And in fact, ironically, the activity is not really looking at students writing down every single factor. We're saying there's an easier way if we just want to determine the quantity. I'm impressed. Somebody's actually written all the factors into the chat. That's pretty cool. That's good. All right, so let's have a look. Once you've done that, could you find another number that has the same quantity of factors? So have a crack at that. And again, I'll just monitor the chat. We'll see if it's as active as what it was last time, because this question is a little bit harder, isn't it? It's like, should I just randomly choose a number? Or is there something common about these? Hopefully you're at least randomly choosing by the way, I should have mentioned all of those numbers have exactly 9 factors. And they all happen to be perfect squares. So 6 squared, 10 squared, 14 squared, and 15 squared. So you could probably start with a square number. Someone has said 256. 256, does that have 9 factors? I haven't listed them, but we're going to find out shortly whether or not that is true. All right, so let's move on. Oh, someone already knows the rule. I'm impressed. But I'm glad that person can't throw it out to everyone. It's one of the reasons why I make it so not everyone can see the chat. It's because otherwise we're just giving away the whole game here. So determine the quantity of factors for each of these numbers. So I'm guessing our friend here that already figured out how many, or the pattern, maybe they've already figured out the quantity of factors or have a shortcut way. So let's try this one. 40, how many factors does it have? And I'll give you a hint already. It has the same quantity of factors as 54, 56, and strangely enough, 875. But I don't think anyone now the person I thought had the formula already figured out. No, not quite. Oh, hang on. Yes, they have. They're still referring to the previous question. That's all right. So we've got 40, 54, 56, and 875. I'm guessing not too many people want to check for the factors of 875. But I'll tell you now, it's got the same quantity as these other numbers. 40 has 8 factors. I think that's probably a fair call. In other words, so does 54, so does 56, and 875. And of course, you know what the next question is. Can you find another number that has exactly the same quantity of factors? Another number that has exactly 8 factors? Well, here's the thing. If I said to you, say, for example, something like x squared plus 5x plus 6, where does it cross the x-axis? I'm thinking a lot of maths teachers would instantly know the answer, but if I gave you some more, let's say, random quadratic like x squared plus 96x minus 400, that's going to be a bit harder. And it's harder because it's not written in a form that's useful for finding out, let's say, the x-intercepts. Just like these numbers are not written in a form that's useful for determining the quantity of factors. So we can't solve problems with the same thinking we use to create them. So if I'm just representing them as whole numbers, as you saw, if that's what we're focusing on, it's not helpful for us to solve it. So let's see if we can recreate or rethink them. So this is where our person that contributed and said, what if we use the factor command on the calculator? Well, the factor command on the calculator would tell us that 36 is 2 squared by 3 squared, 100 is 2 squared by 5 squared, and we said that 196 was 14 squared, so that's 2 squared by 7 squared, 15 squared, well, that's 3 squared by 5 squared, and as our participant said, each of these numbers is in the form of a prime number squared multiplied by another prime number squared. Okay, so that's pretty cool. So my suggestion when you're doing this with students, depending on the year level, is to use some playing cards. Now, when I run this as a workshop face-to-face, participants get a pack of cards, so we can represent it like that. There's a few things that we're reinforcing here, such as 2 squared means that there's 2 2's present, and 3 squared means that there's 2 3's present. And then we want to just move the cards on the table and group them to represent our factorization. Now, remembering the only factors we're going to miss here is 1 and 36 in this case. But if we shift that first 2 off to the side, what we're writing down here is 2 by 18. Now, the other thing that's important here is even though the students are manipulating stuff, they still need to record and document their findings because they're counting factors. So we've got 2 by 18, or perhaps we've got 4 by 9, or perhaps we've got, 12 by 3. And of course, naturally, if I put the the other 2 and the 3, if I move them on to the right, we get the same thing, but just in reverse. And then we've got 6 by 6, and I think we've pretty much covered them all, other than the one I said before, which was the one of the 36. So that's a nice way to actually generate all the factors and reinforces the notion that any factor of a number can be constructed just using the prime factors. So now let's have a look at 100. That's 2 squared by 5 squared. So we've got 2 2's present, 2 5's present. And if you think about what we're doing before, we were just arranging the cards. And I think it should be reasonably obvious as maths educators, we're going to get the same quantity of arrangements. So you can already see this activity is what we call low floor. In other words, students can come in and if they wanted to, just use the factor command on the calculator or reinforce stuff that they did earlier on and writing prime factors, writing factor trees, whichever way you prefer, and just shuffle cards around. I think that's low enough floor for a year 9 class. But the high ceiling now looks at those students could be considering arrangements of things, moving towards permutations and combinations. It's not required, but it certainly gives you a lot of options as to where students might exit this particular task. So now we want to find a rule that determines the quantity of factors for any number given the prime factorization. That's our goal. So it's going to be handy if we have a program that will help us do that. So a lot of people ask, what's this pseudo-coding thing? What does that kind of look like? It doesn't have to be formal like this, but let's just go through what this one's actually doing. So at some point we're required to enter a number. So that's the first step. And then we're going to enter some sort of a loop, and some sort of a counter must be present to count how many times we go through this loop. And there's a condition in the loop that says, is n divisible by, the n being our number that we've entered, is it divisible by 2 or 3 or 4 or 5? If the answer is no, we just go back and continue the loop, and we keep on running through this loop until we get to n, and we'll talk about that shortly. If the answer is yes, then we just increment our factor counter and then continue on through the loop. So each time we see a divisibility does work, then we increment a counter. So and then obviously once we're finished, it just displays the quantity of factors. In other words, displays C. Notice we haven't used words in our pseudocode like input or request or anything like that. They're specific to the language and not required. You can use them. Make sure you use them consistently. We've talked about incrementing a counter. We haven't said whether that's something like C equals C plus 1 or and other variations within different languages. We haven't talked about how we do the divisibility check. Now we're going to use modular arithmetic. Now modular arithmetic's just a fancy name for what's the remainder when some quantity is divided by another. Now if the remainder is 0, then obviously it's a factor. So that's essentially what we're looking at. So freeze frame that in your mind, and let's have a look at what that program might look like on the calculator. So as usual, like a cooking show, here's one I prepared earlier. Let's take a moment to study it and compare it to what you had on the screen a few moments ago. This is the actual code. So we're using the words that are specific to the actual coding language, such as request. In another language, such as Python, which we'll see in a minute, it uses input. So input, enter your number, comma n. That's all syntax stuff. Again, specific to the language and not required for pseudocode. We need to set the counter equal to 0, otherwise we don't know what it is. So adding 1 to it, if C is already equal to some value, then like minus 10, we could get minus 1 factors. Here's our loop for I equals 1 to n. So we're going to navigate through this, and then each time we go through, we check, is it divisible by our number I? So for those who haven't experienced this for loop, and again that's syntax, but a very common one, says that I will equal 1, I will equal 2, I will equal 3, I will equal 4, all the way up until it gets to n. So in here, we're saying, when I say mod, say the remainder, what's the remainder when my number is divided by 1? What's my remainder when my number is divided by 2? What's the remainder when my number is divided by 3, and so on. If that answer is 0, then count it. Otherwise, don't do anything. There's no option, no else, as we would call it, and that's the end of the loop. And that's all it's doing, is zipping through there. And when it gets to the end, it says the quantity of factors is this. So let's see what happens when we run it. It appears here as a variable. Now you'll notice to see the I and the N, they all appear because they're included in the program. We don't have to, we can hide them out, but let's at least run the program. I'll press enter, and it says, what number would you like to choose? 36, and that's it. It says it's got 9 factors. Let's do it again for 100. It has 9 factors, not surprising. 196 and 225. The other ones we had were, what was it, 40? I'd have to jump back to the slides to remember what the other ones were. I think it was 875. Let's see if my memory serves me correct. Yes, another one with 8 factors. Now let's have a look at, now this is a command that's built into the calculator. That's 5 cubed by 7. Now the other one that we had in there was 40. That can be expressed as 2 cubed by 5. Now if you're thinking back to the example with the playing cards, the base wasn't really important. It was, if you like, the quantity of each prime number that seemed to be important. So we've seen 2 different numbers with exactly the same prime factorization. So now it's time to test a hypothesis. And that is, what if I got some other prime number, let's say 11, I'll raise it to the power of 3, and I'll multiply it by some other prime number, and I have no clue what this number is going to be, 22627, but I believe it probably has 8 factors. Now let's see if we're right. So we go variable, factor count, and I want 22627. Sure, got that right? And it says there's 8 factors. Now, obviously we shouldn't stop there and go, oh, we've got the rule, because we haven't got the rule. All we've got is a way of determining whether something has 8 factors. But we did say it had something to do, well, nothing to do with the base, but a lot to do with the exponents. And notice we're encouraging here students to use mathematical language. So it's time to start recording it. Now, I would encourage students to record it with pen and paper, even though they do have a calculator sitting there. But for now, because it's easier, I'm going to just drop it in a spreadsheet. And we saw that if my exponents were 2, then I had a quantity of 9 factors. So I'll call this list exponent 1, and I'll call this one exponent 2, and this one we'll call, I've got to be careful here because I can't call it the name of the program. Now we found that another one had 3, 1, 8. So now that we've got those 2 out of the way, it's probably time to explore some other, and this is where it is a genuine exploration. Students are kind of spoon-fed to start with to get them going. Maybe we should try something that is a prime number squared multiplied by just another prime number. So let's go for 5 squared times 3. So we could find out how many factors it has. So we go factor count, 75, and there's 6. So now I could develop a hypothesis and go, all right, let's check it. 7 squared times 19. Bizarre numbers. There's nothing systematic about my approach yet, other than I've kept the exponents the same. So let's try 931. It too has 6 factors. So 2, 1 gives me 6. So if I put 2 as one exponent and 1 as the other exponent, I get a 6. So the quantity of factors is 6. And I'm trying to establish a rule between this this pair of numbers and this pair of numbers and this pair of numbers and this. And hopefully it's the same rule for all of them. Let's do one more. What's our time? Oh, no, I'm not going to do one more because I'm looking at the time. It's time for a spoiler alert. If anyone knows the answer, you can put that in the chat right now. But I'm going to go over here, see if you can get it before I actually put it in the chat. I'm going to put a formula over here that says exponent 1, and I'll add 1 to that. Then I'll times it by exponent 2 and add 1 to that. And look at that. It gives me exactly the same. So all you do is you add 1 to each of the exponents in your prime factorization, multiply all of those things together, and you get the quantity of factors. Now, if that's as far as the students go, they haven't gone far enough. Let me give you a reason why they haven't gone far enough. Let's change that to a 3 times 5 to the power of 4 times 7 squared. That's a really big number. I wonder how many factors it has. So let's go up here, and this will highlight something else. 245,000. And now you can see it took quite a while. So we've got 60 factors, but here we've got 3 bases. And the question is, does our rule still work? In other words, 4 times 5 times 3. Well, it did. It predicted 60. But I want students to realize all they've done so far is explore a product of 2 primes. What happens if it's 3 or 4 or 5 primes? Does it matter if it's, say, for example, 2 to the power of 3 times 5 to the power of 4 times 7? What happens to the fact that I don't have an exponent up the top, the invisible 1? So our prediction is that would be 4 times 5 times 2, because there's the invisible exponent of 1. So 4 times 5 is 20, times 2 is 40. We're predicting we'll get 40 factors for that. 3, 5, 0, 0, 0. 40 factors. It's looking pretty good. And yes, it does work. The other thing, as I was just saying, is you will find that the bigger numbers, it's going to take a while. That's because our program is actually quite clumsy. When I say clumsy, it's short, but do we really need to go all the way up to n? Couldn't we just go up to the square root of n? Now, when I've done this with students quite often say, oh no, you could go halfway, you could stop halfway, which is that kind of conceptual confusion with the square root. By going halfway, you've gone too far. You're already starting to repeat factors. And for some students, the concept that if you want to find all the factors of 100, you can stop looking at 10 is quite bizarre. If you want to find all the factors of 200, you can stop looking at 14. And students are like, what? No way. But yes, they occur in pairs. And of course, the only thing we want to be careful of is if we went to the square root of that number, you then just have to put in another check routine to say if your number's a perfect square, then we need to add or remove one of those factors before we go doubling it and so on. Now, one other thing I'll show you. I've done the same program. This is done in Python. So you'll see the syntax is a little bit different, but the actual pseudocode is the same. I still have some sort of an input where I'm required to enter a number. I have some sort of thing that's counting. So I'm setting the counter off to 0. I've got this loop And it's kind of weird. The loop is going to n+1. That's something peculiar to Python. And that is, if you set it from 1 to n, it actually stops before it hits n. So when it sees n, it says, I'm out, I'm getting out of here, and I'm not doing it. So you have to go one more than what you might think. It also has this peculiarity is that when you have a list of numbers, the first element is element number 0, which is not so bad because we often talk about subscript 0, the initial position. So it has its pros and cons. You can see there's a double equals thing here. This is I'm assigning C equal to 0. This is I'm testing to see this thing equals 0. This thing, by the way, the percentage sign is modular arithmetic, exactly the same as what we did before. And then we're incrementing some sort of a counter. The other thing that's kind of weird is you don't see an end if, you don't see an end for. That's because you can see from these number of spaces at the start, it automatically indents. So anytime you see it indented, when you get out of that indentation means that that if has finished. So in other words, if I had that, that means I'm out of the if, but still going along in the for loop. But in actual fact, I don't need that. That's it. So if I run this program, Control R, and it says, what's your number? I haven't spaced it out very nicely. You can see it says 9 factors and we're done. One thing you will find out with Python, for example, let's just run it again. And what was that number I had? It was something like 245,000, I think it was. Oops. 245,000. And it took quite a while with BASIC, but the Python's actually a lot quicker. Generally speaking, it's a lot quicker. It's going to make a fool out of me now. So yeah, it tends to run on the calculator a lot quicker than what the BASIC does. But of course, we can still speed it up by putting a square root thing in. The frustrating part with the square root, and I'll show you what it looks like over here, is that you then need to do this checking thing. If it's a square root, then add 1 to the number of factors. This one actually generates all the factors as well. So when I run this one, you can actually see it prints them out. So you can make it a bit more fancy if you wish. Good way to check to make sure your program's actually working. So that's the pseudocode and some actual code. So students write a program to explore it. And then think about the mathematics students will have done in that investigation. And of course, even if they don't find a rule, the fact that they've developed some hypotheses and tested them along the way is also quite powerful. There's a lot of maths those kids have done, even if they don't get an answer, which is interesting because by the time we get to our last one, good luck getting an answer. All right, Euclidean algorithm. This is one that is often used in examples for pseudocode because in fact, it's actually one of the oldest algorithms still in use today, as perhaps the names suggest. It's a very efficient process for determining the highest common factor or greatest common divisor of any two numbers. So let's have a look what the, oh, wow. That's the algorithm. So let the two numbers be A and B. If A equals 0, then the greatest common divisor of A and B is just B, then we stop. If B equals 0, then the greatest common divisor of A and B is A, then we just stop. And then it says we need to write A in quotient remainder form, so A equals Q times B plus R. And the last bit says the greatest common divisor of A and B is the same as the greatest common divisor of B and R. That should be abundantly obvious by now. Perhaps not according to the chat. All right, so let's have a look at a different way to represent it. So I'm going to represent it with two lengths, these two lengths being like having two numbers. So I'm trying to think about if I was going to chop these two lengths up into equal pieces, what is the largest piece that I can chop them into? So in other words, if I chop this bottom one in half, could I then get lots of those and it would be the same as this longer length, or maybe it'd be a bit bigger or a bit shorter? I'm not sure. But what the algorithm says is, you know what? Let's just duplicate, in other words, find out how many times that smaller length goes into the bigger length. But what's left over? So we're interested in the remainder. Should ring true to what we had before, the modular arithmetic thing. Now, the Euclidean algorithm says if you chop these up into little pieces, whatever the size of those pieces, they're going to be the same size in this remainder as what they are in these other little ones. In other words, we can now ditch this big number and say our highest common factor for our original two lengths is the same as the highest common factor of these. Now, you can see that the little one doesn't go into the big one very often. It just goes in once. So there's only a little bit left over. Now, let's have a look. That's the size of the piece that's left over. So now, again, we repeat the process. You can see there's some sort of a looping thing. So our highest common factor, or in this case, the longest length that we can chop these up into so that it'll fit nicely into both, is the same for these. So we find the difference again. So it goes in 3 times and there's a little piece left over. So put the little piece down there, we throw away the big piece, and now there is no difference. There's no leftover. It divides it equally. So we've found the longest piece that we could have chopped these into. Now let's try it with numbers. So I want to find the highest common factor of 200 and 72. So it says, well, just duplicate the smaller length. In other words, how many times does 72 divide 200? Well, it does it twice, and there's a little bit left over. So what it's saying is the bit that's left over will have the same highest common factor as our 72. So we can ditch the 200. Our leftover is 56. So let's get rid of this 200. And it says the highest common factor of 272 will be the same as the highest common factor of 72 and 56. Some of you have probably already figured it out. So let's have a look. There's the little piece. Again, this is a situation where we don't even have to do the division. It goes in once. Let's just have a look at the remainder. And let's have a look. The remainder is 16. So our highest common factor of 272 is the same as the highest common factor of 56 and 16. How many times does 16 go into 56? Goes in 3, and there's a little bit left over. I think most of you would know by now that little bit that's left over is 8. And now you're probably thinking, oh, I can see where this thing is going to end, because 2 times 8 is 16. I have no remainder, which is where Euclid says you can stop. Once the remainder is 0, we can stop. So the highest common factor of 200 and 72 is 8. So our algorithm is complete. And now I think you can see that whatever we chop this 72 up into, obviously it goes into the 8 goes into the 72, and those other bits that would have fit along here, that must have divided them evenly as well. So it kind of makes sense once we see the visual. So if I wanted to find the highest common factor of 334 and 144, let's do it without the visual. We'll do it quickly. So we're saying that 334 is equal to 2 times 144. We have 46 left over. So we want to find the highest common factor of 144 and 46. 46 goes into 144 3 times, and there's 6 left over. So what about this 46? 7 6s are 42, so we've got 4 left over. And now we've got 2 left over. And now we have nothing left over, so the highest common factor was 2. But of course, there are other ways we could have done that. Get the students to do the prime factorization and see if they can get to the highest common factor just from the prime factorization. Now we're going to do some more coding. Let's have a look at what the code looks like for this one. Again, here's one I prepared earlier. That's it. That's the entire program. Now let's see if we can relate it to Euclid's algorithm. Euclid's algorithm said if A equals 0, then stop. If B equals 0, then stop. Well, here's a really efficient process. Oh, by the way, this one's doing the greatest common divisor or highest common factor of 3 numbers. So let's just start with the 2 because you'll see what I've done in a minute. So that pretty much covers us for the first bit. The first 2 steps in Euclid's algorithm, because we're using the, I guess you could say the null factor law, that if A times B equals 0, then either A or B equals 0. So as long as that product is not equal to 0, then neither A nor B could equal 0, therefore we need to proceed. Now, if A is bigger than B, this is just so that when we do the division, it works correctly. So if A is bigger than B, we divide A by B, and that becomes, in other words, the remainder becomes our new A. Otherwise, in other words, B is bigger than A, when we divide B by A, the new remainder becomes B. And we get left with the smaller number, which was A. That's it. And then it displays A and B. Now, to do 3 numbers, which goes beyond what the calculator can do, the calculator, using the highest common factor command, will only do 2 numbers. Now, all I've done is just basically copied and pasted that whole thing down and said, okay, if A equals 0, then the new A is equal to C. Otherwise, it's equal to B. In other words, what I'm doing is saying, well, which one of those numbers from my past example was equal to 0, the point at which we stopped the algorithm? Whichever one was equal to 0, I'll swap it in for a C. And then I just literally copied and pasted that whole thing down here again. So if I wanted to do 4 numbers, A, B, C, and D, I could copy and paste again and just say, well, which one of these is 0, swap it out for a D, and then paste it in. Which means, and in the investigation, students go on and do a list of numbers. You can see that we're repeating this. So the challenge in this particular investigation is for students to go through and find the highest common factor of an entire list of numbers. So extend what they're doing here. And this notion of, well, I've got this little algorithm that I'm doing and all I need to do is repeat it. So you could actually define this algorithm as highest common factor and then just repeat highest common factor of AB, highest common factor of BC, highest common factor of CD, and so on. That's it. That's the entire program. And as I said, represent the numbers in prime factorization form, and students will see there's some other connections that they can be making. All right, now it's on to the scary stuff. Euler Totient function. I promise it's not so scary. It's just super cool. All right, so let's have a look. What does it do? The Euler Totient function counts how many numbers are co-prime up to our value n. Let's see if we can throw some numbers at it to get a better understanding of what it's about. So the Euler Totient function for 12 is equal to 4. That should be abundantly obvious now. Oh, no, it's not, perhaps not. So when we're talking about co-prime, what we mean is, do they have a highest common factor other than 1? Notice how it links to the previous activity. So what is the highest common factor of 12 and 1? Well, that would be 1. So we need to count it. This Euler Totient function is a counting thing. So what's the highest common factor of 12 and 2? Well, it's not 1, it's 2, so we don't count it. The highest common factor of 12 and 3 is not 1, so we don't count it. The highest common factor of 12 and 5 is certainly not 1. The highest common factor of 12 and 5 is 1, so they're co-prime. 6 is not, 7 is not, 8 is not, 9 is not, 10 is not. 11, the highest common factor of 12 and 11 is 1, and therefore we count it. So we have 1, 2, 3, 4 numbers. I could have put the 12 in, but I'm hoping most people can see it's obvious. The highest common factor of 12 and 12 is not going to be 1, so I haven't bothered to put it in here. And the same applies when you're doing the program. You don't need to go up the way up to n. If you're thinking about the Python coding, it purposely excludes the last value, so our loop can go from 1 up to n, and it will naturally leave the n off, so it's no big deal. So that's our Euler Totient function. It counts stuff. Now we could write some code to do that. Well, because I knew the time frame would be somewhat problematic, let's have a look. So I created this variable called data. You can see I request the number n. Now this is going to do a lot more than just one Euler Totient value. It's actually going to do a whole stack. So let me just go back to this bit. That's the bit. So here's the bit that actually does the Euler Totient value. That's it. 1, 2, 3, 4, 5, 6 lines of code, 7 if you want to actually see it. So it says, I'll go from I up to J, whatever our selected number is. And if the greatest common divisor or highest common factor equals 1, then count it. That's it. That's the code right there, that little bubble there. So what have I done here? I've put this into a nested loop. So I'm actually going to find the Euler Totient value for a whole stack of numbers, a range of numbers. So when I say, let's do the Euler Totient function for 12, it'll actually do it for 1, 2, 3, 4, 5, 6, 7, all the way up to 12. It'll work it out for every single one of them. So let's give it a crack. We'll go Euler Totient function. Oh, I did up to 200. Let's go up to 12. So you can see it's doing it for each one. So the Euler Totient value for 12 is actually 4. Interesting. The Euler Totient value for 11 is 10. The Euler Totient value for 9 is 4, and so on. So let's go back and we'll do it for 200, like I did before. And you can see it's going to whiz through these numbers. There is, by the way, a quicker way to work this out, which we'll see in a moment. But for now, let's just watch it tick over. We've got plenty of time to watch that tick over. It's doing the Euler Totient value for the first 200 numbers. And then we'll have a look at what that looks like on a graph. Because the code, as you could see, is pretty simple, right? There was like 4 lines of it, unless you want to do it for a whole family of numbers. So let's go on to the next page. Oh, look, there's the Euler Totient value for the first 200 numbers. And if I had the microphones turned on for everyone, hopefully I'd be hearing that. Ooh, that looks cool. So if you hover over one of these numbers, so the Euler Totient value for 89 is 88. The Euler Totient value for 53 is 52. The Euler Totient value for 31 is 30. Hopefully you're already figuring out what these numbers are. The Euler Totient value for 599 is 198. Let's check something, shall we? Factor 199. Oh, look, is prime 199? Yes, it is. In fact, I think I'd be fairly safe to say that all of these numbers up here are prime. And the Euler Totient value is just one less. So think about that. If you're testing a prime number, how many factors did you think it would have, or how many coprimes did you think it might have? There's another group of numbers coming through here. So there's a pattern in here. These sorts of numbers, you've got to be careful to make sure they're all on the same line, like 128.64. 106.52 is probably not quite on that line. There's a couple in here. So what's going on with that line? There's certainly a bit of a pattern going through here. What about these numbers down the bottom? 30, 36, 42, 60. The Euler Totient value for 60 is pretty small, right? It's only 16. And look at some of these ones. This number here is 150 and its Euler Totient value is only 40. Well, the Euler Totient value for 100 is actually 40. So for 150, that's a pretty low score. In other words, it must have a lot of factors in it. And guess what? It too is related to prime factorization. When you're writing that program, hopefully you've seen that if we're just using this highest common factor command, we're already doing some chunking. We're already going, oh, I have a program or routine for that. What patterns do we see? Well, we saw some prime numbers sitting in there. The bottom numbers, see if anyone can put it in the chat. What were the bottom numbers about? And then, remembering this Euler Totient function count stuff, check this out. Now let me explain it to you. The Euler totient value for 12, so if n is 12, we go from 1 to 12. We're going to find this product. We do 12 times 1 minus 1 over pi, where pi is each of the prime factors. So for 12, we'd see the product 12 times 1 minus a half times 1 minus a third. So that's a half times 2/3 times 12 equals 4. So for 100, we can do 100 times 1 minus a half times 1 minus 4/5, which gives us 100 times a half times 4/5 gives us 40. This is a shortcut way of working it out, and it's a product. It's actually to do with expected values. I'll leave everyone to figure that one out for themselves because we've got 5 minutes left. Oh, someone's put some nice stuff in there. Oh, square root. I'm going to have to read that one back. Oh, and someone else has asked, can I get a copy of the slides? Absolutely, you can. Not a problem. In fact, before I go on any further, let me just show you where you can get these things. On the TI website, if you want your students to do some actual coding, there's free lessons. They can choose Python or Basic. Now, because we're doing this particular activity this week on our webinar program, the activity of the month, let's check. Oh, look, it's code by numbers. So here's the complete series of the 4 activities. If I just click on that, it'll download the Python version of them all. If I click on that one, it'll download the TI basic version for TI-nspire. If you're using a TI-84, that will give you the basic version, and TI-84, that'll give you the Python version, or you can just go to any one of these activities. That graph should now look familiar. A little Euclid character down there. If I just want one of the activities, and I can click on there, and you can see it's going to give us an overview. It's telling you this is Act 4 or Activity 4. It's telling you the sorts of coding that students will be doing in it. You can download the PowerPoint for it. You can download the teacher notes and answers, don't show the students, and the student activity. So they're all up on the website. Go to the home page and select Activity of the Month, and there it is. All right, let's go back to our highly composite numbers. What on earth are they? They actually had a little showing in our Euler totient function. Basically, the highest common factor, the highly composite numbers rather, is a number that has more factors than all its predecessors. So what does that mean? Well, let's start with 1. That would be a good place to start. It has more factors than its predecessors because it doesn't have any predecessors. So it's kind of like winning a race when you're the only person in it. So by default, it's a winner. Let's have a look at 2. Well, it didn't have a lot to beat, did it really? There was only one other person to beat, and it had to beat 1. It's got 2 factors, so it has more than all its predecessors. So it too is highly composite. 3, not surprising, it's prime. It was never really going to, well, so is 2, I guess. I get that. But, you know, we're not going to see any more prime numbers amongst us. So it only has 2 factors, which is not more than 2, so therefore it's not highly composite. It's a dud. We can throw it out. 4 has 3 factors, beating its previously high composite number of 2. Still not a big challenge. 5, well, again, it's prime. Didn't think much of that. Let's try 6. It has 4 factors, so it beats 4, which was the previous highly composite number, with just 3 factors. So far, the quantity of factors has gone 1, 2, 3, 4. Perhaps the next one has 5, but students should realize that would mean it has to be a perfect square. And 12 seems to have quite a lot of factors. So I'm sort of sensing that 12 is our next highly composite number. But could we prove it? Could we show it? And it means that you've got to go back and check every other highly composite or every other number up to that number, which is the reason why you want a very fast or efficient factorizing program. So here's one I did earlier. So in this one, I'm keeping a record of the highly composite numbers and the quantity of factors for each. and some sort of a high score. So you can see here my record is a high score, and that's it. That's the entire program. It's doing a factor count routine, and then away it goes. So let's have a look. And remember, you could have called up your factor count routine and said, count the factors. What have I got? Is it better than my previous record? No, toss it out, go to the next number. So let's try highest HCN. And I'm not going to go to 6,000. Let's just go up to 200. There's all our highly composite numbers up to 200. The first one has 1, then 2, then 3, then 4, 6, 8, 9, 10, 12, 16, 18. We skipped 14, which is weird. We did get a 9 in there. That's kind of cool. And there shouldn't be many surprises amongst this. 36, 48, 60, 120, 180. These are numbers that we'd kind of expect to be having a lot of factors. Let's go up to 600. We didn't get a lot more, did we? Previously, we went up to 180. We only got 2 more. So obviously they're not as close together after a while. And guess what? You should also have a look at the prime factorization of each of these, and you'll start to see some patterns. I'm not going to go through these patterns. That's what your student should be doing. But I can tell you, if you find it difficult to summarize and find a general rule for highly composite numbers, then you can join the frustrated mathematician, very, very good mathematician of Ramanujan, because he looked at the prime factorization as a way of trying to find out what or can we predict the next highly composite numbers. And every time he thought he'd found a pattern, it sort of messed up and didn't work anymore. So it's one of these, in this particular investigation, we're not expecting students to come up with an answer, but we want them to develop some hypotheses and test it and see that it works, and then it stops working. It works and it stops working. And nobody has found a rule yet. So, not expecting any students to find it, but pretty impressed if they do. All right, and there we go. You can see the program is going to make it pretty quick. But you can also add a level of artificial intelligence to it. Because once you start to get patterns, you'll realize I don't have to, if I found the highly composite number at 60, I don't have to check 61 or 62 or 63 or 64. There's ways you can actually increase the step counter so your program can get more and more efficient. But speaking of efficiency, we're out of time. So that's all we've got for this evening. Now, our next webinar is focusing on parabolas. And I highly encourage people to join in on that webinar because I have a giveaway. The very generous Matt Parker wrote a brilliant book. If you haven't got it, join in our next webinar because he's autographed his book and we get to give away an autographed copy of his book called Humble Pie. It's an absolute brilliant read. It's a book filled with, we'll say, comical versions of mathematical errors in the world. And sometimes they've led to some pretty ordinary results, shutting down airports and all sorts of things. And we're giving a signed copy, an autographed copy of his book in our next webinar. And it's going to be similar to what you've seen tonight. That is mathematics done a little bit different, but again, you'll have all the activities, all the worksheets, all the PowerPoint slides done for you that you can just click and download. So I can see everyone saying thank you. In other words, Peter, it's time to be quiet and send everybody off to get their cup of coffee or cup of tea. Thanks for joining us, and hopefully we'll see you on Focusing on Parabolas, our next webinar.